is not muted. I slightly changed 1.3 from what we did last year. So I very briefly took a kind of look into what we're going to cover at the very end, which is going to be piecewise functions. I have substituted that out for, we're still going to talk about piecewise functions, but we're going to look at a very specific kind of piecewise function. But I need to update my recordings. So we'll be running through that here. But before we get to kind of the end of 1.3, we're going to talk about two different function, like broad classifications for functions. This first one actually does come up. It'll come back up when we start working with our trigonometric functions. These kind of adhere to this particular idea. And we're going to see the other one definitely gets used a fair bit in calculus, so I want you to be kind of aware of that. It's a very broad classification. We're going to be looking at a very, very narrow subcategory of these types of functions, but I also want us to kind of have this kind of loose understanding of what we're seeing. All right, so let's start with an example. Okay, so I'm going to give you guys two functions here. Good. My question for you all is, it's pretty generic. What do we make of these functions? What do we notice about the blue function? What do we notice about the red function? Any kind of details that we can maybe enumerate on? What do you mean by that, Jen? Okay, so something about them looks maybe a little bit similar. If I were dividing this graph in half, what side would you say looks very similar? All of the stuff left-hand side. This side here. Okay. So we've got, I think that's kind of to Jen's point, what we're talking about with the reverse. Like we've got on one hand, maybe both of my functions are going up towards positive infinity. And then on my negative side, on my negative values, maybe we have one side that's going towards negative, one side that's going towards positive. So maybe is that the reverse that we're kind of talking about here? They're going in the opposite directions, but only on the left-hand side. It's actually a fairly astute observation that is certainly going to play a role. What else can you say? Yeah, this is an interesting idea that we haven't really talked about yet. We haven't covered transformations. That'll be 1.6. That. But absolutely correct. We have some symmetry here. Right? In particular, this idea of if I look at my blue function, how if I were to reflect it about the y-axis, which is to say, if I were to take all of my x's and make them the opposite sign, that's physically how you would reflect them, notice that I would end up with the exact same function. That's an interesting observation. Now, the other one I think almost reflects about the x-axis. It's really close. If I were to actually reflect, think about like taking it and rotating it around the x-axis, I think I'd end up with maybe something like this, which is really, really close to the original function that we're starting with. Thank you. But it's kind of it's hard to see here, but it's kind of the, again, kind of the reverse, which, you know, I would stray away from. So reflection about the x-axis doesn't quite describe our symmetry. But after a reflection about the x-axis, if I were to then also rotate it about the y-axis, so like do both x and then also y, then they might start to, we would get the exact same image. And that is actually very true, right? If I were to then rotate it again, we would absolutely get the same thing. Right. So yes, I agree we have symmetry. Now we might maybe call this reflection about the line y equals x would be a way to reflect about both x and y. But absolutely, we've got some symmetry that's going on here. That's really, really important. Does anyone know what these graphs would go to, like what they look like, what their function might be? It's actually like we can't say definitively, but what do they remind us of? Yeah, go for it, Ashton. Yeah, I think that looks a whole lot like x squared. What about g of x? Yeah, x cubed could be pretty good. Now, x to the fourth could also be for the blue one, x to the fifth could also be for the red one, but certainly they kind of remind us of these functions. Okay. Now, I want to actually discuss what this symmetry idea would kind of translate to algebraically, because I think Braden's point is really quite wonderful here, that we have some kind of symmetry. But how does that translate into a property that I can describe about functions? What does that mean for me? Well, what does it mean for me to be able to have symmetry about the y-axis? Or if I were to take this image, rotate it around the y-axis, I stay the same. What do I notice about my y values if I start from the origin and move to the left or to the right? What's going to be true? They're the same. The y values match up when I'm comparing a positive version of x with its negative version. In other words, maybe for our blue function here, we might say that f of x is the same, the output is the same when I plug in negative x. In other words, something's happening that's kind of erasing the effect of putting in my negative x. And when we look at what this function really looks like, x squared, why would it not matter whether I plug in a positive x or a negative x? What's going to happen to it when I put it into this function? It's going to always become positive, right? A positive number squared is positive, and a negative number squared is also positive. So we're doing something to the machinery here, something about the machine is erasing kind of the effect of whether I'm plugging in a positive number or a negative number. We see these same outputs across the board. Okay, what's going on then with g of x? I'm looking at this particular function. If I'm looking, starting at 0, moving to the right, moving to the left, again, we do have some kind of symmetry, but it's not that the negative isn't having an effect. What's going on here? What's happening to our y values as I move to the left versus to the right? Yeah, so yeah, we're getting negative outputs relative to the positive outputs that we are getting otherwise. And so if I plug in the negative version of x, I'm going to get the negative version of the output. How could we maybe write that in terms of what we see here? Well, this is, again, what are we doing? Well, we're plugging in the negative version of x. And again, we're saying, well, that's going to give us the negative version of the y value, negative g. This is not a property that is exclusive to exact x squared. This is not a property that is exclusive to x cubed. This is something that's a lot more universal than this, and it ties really, really closely to the symmetries that we observed here. Basically, anything that follows symmetry, like what we see with fx, is going to also carry with it this definition. It's kind of what this symmetry actually means. And anything that carries the symmetry that we see with g of x is going to carry this definition. Now we have special terms for functions that follow these particular properties that have these symmetries, but that algebraically have this kind of trait of plugging in negative x either leaves me the same, doesn't do anything to my output, or swaps my output to the negative version of the output. And these are called even functions and odd functions. Does anyone know, or does anyone care to guess which one of these would be even and which one of these would be odd? Yeah, go for it, someone. X squared, we would say maybe that this function is even. That is correct. And this would be odd. Why'd you guess that? Or did you just know the definitions? Or is there something that we learned it before? Okay, super fair. Why might we call this function even? What might clue us in that this might be an even function? Yeah, the exponent is kind of what we're looking at. Now, are there functions that don't have exponents that would still follow these classifications? Absolutely, absolutely. A very important one that we are going to look at is that sine of x, and I don't need you to know this now, we will review it later, is an odd function. Is there an odd exponent here with sine of x? Not really. It's not something raised to a power. Okay, maybe you could argue one, but then I would go around and tell you, okay, but then cosine of x is an even function, and there certainly is not an even exponent that we could attach to cosine. So it's not exclusively referring to the exponents that we see, but if we see exponents, it's a pretty good clue as to what we're looking at. If I see, oh, I'm working with x squared, or oh, I'm working with x to the fourth, or oh, I'm working with x to the sixth, we call those functions even because they kind of share these properties with the kind of baseline polynomials that we start with. Likewise, if I'm working with x to the 1 or x cubed or x to the 5th, these are going to kind of fall into our odd. Again, not all encompassing, but kind of a nice way to clue us into what we would expect. And these properties that we have defined are actually what it means to be even and what it means to be odd. They also provide us with a litmus test to determine if what we are looking at is even or if what we are looking at is odd. If I plug negative x into my function and it stays the same, it's an even function. If I plug negative x into my function and I get the negative version of my function, it's an odd function. That is not just a property, that is the definition. So we might say here, even function, this is anything where f of negative x is just the same as f of x, right? It doesn't matter whether you plug in the even version or the positive version of x or the negative version of x, you're going to get the exact same thing. And my odd function, f of negative x, is going to reverse my output, quote unquote, reverse my output, give me the negative version of my output. Exactly. Okay, now if my output were negative, that would mean I'm getting a positive. So just to be clear, when I'm saying like the negative version of x, if x is -2, then the negative version of x is positive, right? We kind of look at this and think, ah, yes, of course, f of x, this is a positive output with a positive input. We don't know, right? This might be our function might be, negative x squared, which would be the same thing, but, both sides pointing down. And we run into the exact same thing where, like, yeah, the signs of our outputs kind of line up regardless of what our exponent is. So let's take a look here at example 2. Our goal is to determine whether what we are looking at is odd, even, or entirely possible, even. Entirely possible that when we plug in negative x, it's just not going to behave in a way that we can really do. Which is totally fine. So starting with example A, just judging from like our words, odd and even, what would we predict is going to be true for, should this be an odd function, an even function, or neither? We'd probably predict even, and what's kind of cluing us into that? The exponent here, the fact that this 4 is an even number, maybe means that this is an even, or probably means that this. But what's our check? What would I do to confirm whether or not this is in fact an even function? We need to put not just a negative number in, we need to put negative x in, like literally the expression. Do you guys remember 1.2, what we were doing 2 days ago when I had you plug in like 0, I had you plug in negative x, I had you plug in x plus h? This is the why I was having you plug in negative x. Here it's relevant. Here it's like actually the thing that we need to do. So plugging in negative x, we need to, again, evaluate what is this function going to look like. Not f of x, we need f of negative x. And as long as we're precise with our parentheses, we should be okay here. F of negative x, 3 times negative x to the 4th. What is negative x raised to the power of 4? What's going to happen to my negative here? It's going to become positive, right? A negative times a negative is a positive. A negative times a negative is a positive. 2 positives multiplied together would be a positive. And so this is going to be 3 times x to the 4th. What do we notice about what we ended with versus what we started with? They are the same. Absolutely. And so if plugging in a negative value for, not a negative value, but literally plugging in negative x, if that didn't change my output, what kind of function is this going to be? This is an even function. Very good. I want to highlight something that Oliver mentioned. I saw this in 5th period yesterday as well. So just wanted to not that it's not necessarily going to work, not that it wouldn't necessarily be a decent check for it. I just want us to be a little bit careful. When I plug in negative x instead of x, what I get is effectively proof that this would work for all values of x. So it doesn't matter what x value I pick. I could pick 10,000, and this is actually sufficient to know that I'll still have this property when I plug in negative 10,000. I don't need to actually compute it, showing that if I take a generic x versus a generic negative x, plugging in the opposites gets me the same result. That should always. Now, the suggestion, which I think is a really good suggestion, which might even computationally be a lot easier than what we did in certain cases, here it wasn't too bad, but in certain cases might be computationally a lot easier than we did, would be to, let's try plugging in +1, and then let's try plugging in -1 and see if we get the same answer. That's not a bad idea, but we run into this logical problem of, if I'm trying to prove to you that it rains every single day this week, would pointing out the window and saying it's raining today be good proof of that? No. Now, does pointing out the window and saying it's raining today mean that the claim that it's going to rain every day this week, does that mean that that claim is wrong? Not necessarily, but what am I missing? I need proof that it's going to rain on the other days, right? We have good confirmation that yes, at least one of the 7 days were good, but we've missed checks on, Thursday, Friday, Saturday, Sunday. So we want to be very careful with plugging in just like one particular value. It's possible that you plug in 1 and -1, and it just so happens that you get the same answer for a function that's not actually odd or that's not actually even for every single value. Entirely possible. You'd have to get pretty unlucky, but you could get unlucky, right? It's entirely possible that you get unlucky. Now, again, it's not a bad test. Like it needs to be true. Like -2 and 2 need to match up in order for this to be true. And you're probably not going to get unlucky if you do it. But just I want us to be clear that like logically that's it's not quite robust enough. It doesn't quite do what I want it to do. And if I am claiming that this should work for every value of X. And the problem is like I can check either my weather app or I can go outside and see if it's raining every single day this week. Can I plug every single value of X possible into this function? No, why not? Infinite number of X's in fact, right? Even just between the numbers 1 and 2, I have an infinite number of X's that I would need to check in order to know for certain that is the case. And so keeping it generic, plugging in very literally a negative X is going to be the, I would say, the optimal way to go about it. Not a bad idea from Oliver. It probably would work. It probably would work, right? If you plug in 2, you plug in -2, you get the same thing. That's pretty good evidence that it's going to be even, unless you just got really unlucky. But I am warning you that you can get it. All right. Let's take a stab at B, and then I'm going to give you guys a chance to work on C and D here. Looking at B again, just right off the bat here. What would we predict? Do we think that this is going to be an even function, an odd function, or even? What makes us say oh? Exponent. What are the 2 exponents that I'm working? So 1, remember 2x to the 1 here is like an implied 1 minus x cubed. Absolutely correct. We are working with 2 odds. Now it's possible, like each of these individual functions is probably going to be odd, but maybe like an odd plus an odd gives me something else. We're going to see that that's not the case, that an odd plus an odd will always give us an odd, which is nice. Kind of like how a negative number plus a negative number will always be negative. An odd function plus an odd function will generally, not generally, will always be odd. But how do we check? All right, I can say that because, you know, I've done the proof. But how do we check that it works with this? What do we have to do? Plug in -x. So g of -x is equal to 2 times -x minus -x cubed. 2 times -x is just going to be -2x. Okay. And then the -x here cubed, right? We have to do order of operations. So first we do the exponent. What happens to -x when I cube it? Is it going to become positive or is it going to stay negative? Negative times a negative times a negative is going to get me, what we say, a negative. Very good. And then I'm subtracting it. So then what's going to happen? Then it's going to become positive, right? We're subtracting a negative x cubed. And so we are going to add x cubed. Could I have at this step right here done this? Could I do it like that? Before I cube everything? Multiply by -1 before I apply the cube? No. All right. PEMDAS, exponents, then multiplication. Think of this minus is literally multiplying by -1. So in order to do this, I need to apply the exponent first, right? If that was a to the 4th, the negative is going to go away already. And so I don't want to switch it to addition. It's going to stay as subtraction. So just being careful with our order of operations here. What do we notice about this function compared to this function here? It's kind of like the additive inverse. Right? Notice how positive 2x has become negative 2x, and how negative x cubed has become positive x cubed. So even though we have a positive in here, that's still good. That's a sign that we have done something correct, because it started out as negative x cubed, has now switched to positive x cubed. This is in fact the same as negative g of x. And so what kind of function are we dealing with? Odd. Our predictions from the get-go were absolutely correct. All right, take a stab at C and D. My advice for D is that this squared is deceptive. I did that on purpose. So I would recommend actually like doing it as x minus 2 times x minus 2, do the multiplication, like boil it out, and then see what you end up with, make your prediction. Is it going to be odd or even? Rather than just looking at that 2 and being like, oh yeah, it's going to be even. Or you could plug in negative, again, you could plug in negative x. Even that. What'd you do? So when you plug it in, you first have to evaluate what's going to happen to the companies. You're not going to like be able to find inputs in that way. You're going to check what's going to happen. Yeah, now what's going to happen. But it's an f of x even function because it's g of x thing a function. And like here's the yeah. So for C, the f of x and g of x that it's referring to are a. Okay. Yeah. Well, sure. But yeah, your methodology is okay. So if our f of x here is this f of x, what is f of negative x going to be? Or you could actually like do the multiplication. Either way is fine, but the way you're doing it is like really good for like the proof. Yes. Yeah, so what do we end up with here? Why do you say that this is? I agree. Why do you say this is anything? Yeah, notice here that we end up when we do the multiplication, right? We've got the next squared, which is going to behave for even. We've got this like negative 4x, which is going to behave odd, and then we've got this plus 4, which is also going to behave even. What's the power that's attached to the plus 4 next to the 1? It doesn't have x, so next to the it would actually be x to the, yeah, you could think of it as like 4 times x to the 0. And that's why it fits that even definition, is because it's like x to the 0. Yeah. So you'd absolutely right. This is what we can do. And then you could use the previous ones, the fact that f is even and the fact that g is odd in order to continue. Use the property that f is here, the property that is odd, to see what this is going to become. Because with if the negatives are just sitting in the inputs, we can't really tell necessarily what's going to happen. Deal with the options. Okay, so notice here. Okay, so you plug in your. Okay, yeah. So this is this looks great. You plug in negative x, which is great. You missed parentheses here. And so what's going to happen? You're going to take negative x squared, a positive x squared. So notice how this part of my function, right, x squared stayed x squared. But negative 4x being positive 4x, so this behaved like this behaved like and notice how plus 4 stayed plus 4, so that behaved like the fact that like some of it's behaving even, some of it's behaving odd is meaning that it's down. It's not always going to be like some's behaving odd, some's behaving even. But in this case, that would be
So like the whole problem changes.
exactly. So notice for B, it's because both the negative 2x and also the x cubed, because both of those flip flopped, that is an odd function. Yeah, very good. Okay. First one looks good. How'd you get it was going to be odd? How'd you get it? We're correct. Yeah. Yeah, that's, yeah, right, because this is gonna be like a positive version times a negative version. Well, it's gonna be positive times negative gives us. It's negative, sorry. So f of negative x is gonna stay the positive, right, because it's even. G of negative x is gonna become the negative because it's odd, and a positive times a negative is a negative. And so absolutely correct, so it's done. Yeah, and your D looks great. Yep, looks super good. Yeah, I could notice here, we've got like some of it looks like gonna behave even, like the x squared bit will be even, but then like the negative 4x is gonna behave odd. And then the plus 4, well, that's gonna behave. I mean, this is gonna stay the same number that we plug into. X. You did out the multiplications?
That's where the aim of total E is product.
Yeah.
About the revision.
How we doing? How could we check for C? What would you do to check? Is this? Very good. And then I would use the two previous examples to see if one's going to be true about Patton's number, so it's going to be true about it. So that's how I do. What happens to is G an even function? G was right. This function right here. So I'm using the f and G that we have above. Notice f is even. G plus we found those off. Those are the. This looks super good, and then use the f and G. And you can do out the multiplication, or you could just use the fact that when it's even, it's on a sticker. So I would say, so you can't distribute the square. This was the problem I figured out. You need to actually like boil it.
Oh, so like x plus 2.
Yeah, and I would stay away from plugging in negative x first. I would wait until you plug it out and then plug in the negative x. So which make it like
Yes.
Yeah. Yes, exactly. If some bits are like even, some bits are like odd. No, you're,
might be.
this is correct. So because notice here, it's the negative of at G. So you're totally correct in this. Yeah, but for this one, here, this is x squared, it's gonna be like even function. The 4x is gonna be I'm squared.
Yeah, it might be people do the way you got to do
Yeah, it's not like
solve it.
That's what I need.
So I guess it's the same.
Yeah, so we're like adding a bunch of even functions together. Exactly. Yeah, think about how like a positive number plus a positive number plus a positive number is always going to be positive. Similarly, yeah, exactly. Similarly, that is one. Sometimes it's just not going to behave in any kind of pattern like that. A good example would be like, we looked at the function 3 to the x. If I plug in negative x here, I'm going to get 3 to the negative x, which is the same as 1 over 3 to the x. This is not behaving even. It's not the same, but it's also not behaving odd because they're both positive numbers. And so it's just doing something. It's possible that we could run this. So there are other types of neither, but you're totally correct. And even plus an even plus an even plus an even plus an even is always going to be even. Likewise, odd plus odd plus odd plus odd plus odd, always going to be odd. But as soon as you start mixing the two, that's when that is a case where it throws. So I will say for that one, if I can't your big square, so I just can't, that square doesn't, you have to like spoil it out. Or do that one.
Yeah, what you see?
Yes, unsquare looks like very what's the negative. Lots of negative. Negative plus a negative. Yeah, so that one is extremely negative 4x there.
Okay.
And then that'll double jump like that. But yeah, that was constructed. Yeah, which I really just. Okay, let's take a look at these. I did give you guys the two tricky ones. So this, but you guys did really well. I'm really happy with what I'm talking. Two different approaches that I saw for C. One approach, which I thought was great, was people took the function fx. They took 3x to the 4. And they multiplied it by 2x minus x. If I'm going to multiply things like this, right? I have base to a power times base to some kind of power. What do I do with the powers? We're going to add the powers here. So what is this product going to look like? X to the 5th minus 3x to the 7th. What do we notice about our exponents here? They're odd. And so what would we predict this function to be? We would predict that this function would be odd. Right? So that's one way to do it. You plug in negative x and the negative, this becomes negative 6x to the 5th, and this becomes positive 3x to the 7th. That would work. Absolutely. That's great. Okay. Now, I only really saw like 2 or 3 people do that, though, and that's fine. That's great. It's actually not how I would solve this, but I think that's a perfectly valid way to go about doing it. What I saw a lot of people do, which just made my math major brain very happy, was people left it generic. They left it as is, and they said, oh, well, I need to know what h of negative x is. And h of negative x, what am I being asked to do? Everywhere I see an x, I'm just replacing it with negative x. This is going to be f of negative x times g of negative x. All right. Well, what do I know about f of negative x? What is this the same as? This is the same as f of x. Why do I know that? What property do we have of f of x? We know it's an even function, right? We know that if I plug negative x into f up here, that I get the same thing. It stays whatever sign is going to say, stays positive. So this is even, or at least this piece is even. So we get f of x And then what happens to g of x when I plug in negative x? It's odd, and so it becomes negative g of x. And positive f of x times negative g of x is equal to positive times negative gives me a negative f of x, g of x. How does negative f of x, g of x compare to what we started with? Well, notice that this is the negative version of h. Why did we see that? Well, it's because of positive times a negative is a negative. And so it makes sense that this negative becoming function, this odd function times an even function that's going to stay positive, would net us a negative. And we could show that this is actually the way that you guys, that I saw a lot of people do this. Nice. This is generic, which means it works for any even function and any odd function. You've just proven that an even function times an odd function is always on. No matter what those functions are. So yeah, we could do it specifically for what we see, and that would get you full mark, like full credit for this question, and that's great. But we've done more than that. We've gone above our pay grade. We've shown that it works for every single function that is odd times even. And again, this is because very similarly, just very similar to this idea, even and odd functions really tend to behave like positive and negative numbers. So for instance, if I took two odd functions and multiplied them together, what kind of function would we expect at the end? We expect an even, right? Two negatives multiplied together give me a positive. If I took two even functions and multiplied them together, what kind of function would I expect at the end? Also an even, right? Two positives multiplied together should give me a positive. What if I take an even plus an even plus an even? What should I end up with? What's positive plus positive plus positive? That's a positive. That's going to be an even. What about four odd functions all added together? What's negative plus negative plus negative plus negative? Plus, plus, plus. Negative plus negative plus negative. That is going to be a negative. So I can add or subtract positive, or rather not positive numbers, but even functions and always stay even. I can add or subtract odd. That's kind of why we can do like what we saw with b, where we're like, okay, 2x is an odd function. X cubed is an odd function. If we combine them through addition or subtraction, we still have an odd function, which is nice. Okay. Now D. For D, my advice was that I'm trying to trick you here. I intentionally made D to be tricky. Looking at it right off the bat, what's our temptation? If I gave you 2 seconds to label this, what would we probably say? I would probably say even, and what's the clue to that? The squared, all right? And that's the trick. That's why that's what I'm trying to do. And so what was my advice? Boil it out. See what we get when we do the multiplication. Whenever you see something like this, it is not a bad habit to write it like this, because it'll make it a lot more clear what you need to do. Now you can do your Punnett square, you could FOIL, whatever you feel comfortable with. I do not care. What we at Collierville have been trying to pretty consistently show is this like Punnett square thing. But again, whatever way you have is perfectly acceptable. And so for this, I get that this is x squared minus 4x plus 4. Pause here. Do you feel okay about how I had gotten to? Okay, so where did I lose this? For this? Like what I'm doing here? Do you do foiling, Samuel? when you multiply like binomial times binomial? Like first, outer, inner, last? Okay, so you can do that, and that's totally fine. This Punnett square thing works really, really nicely for the thing that's really nice about it is you can use it for larger polynomials when you're multiplying them together. So it works well for binomials, but it works just as well for trinomials. It works just as well for anything that is larger. So this is kind of what we've defaulted to see. You make a Punnett square out of the pieces that you're multiplying together. So x and then the -2 and then the x and then the -2. And you're just multiplying everything you see and then adding up all the boxes. So x times x gives me x squared. X times -2 gives me -2x. -2 times x gives me -2x. And then -2 times -2 gives me +4. And then adding everything together, we end up with x squared minus 2x minus 2x plus 4, and then minus 2x is combined to give you -4x. Don't distribute the squared. It'll make me sad. Yes. Great. Yeah, so you plugged in the -x first. Hard to then evaluate what's kind of going on. It doesn't simplify super well. And then you did the Punnett square, right? Or did the foiling or whatever you wanted to do. That's fine. You just don't have a nice solid basis of comparison. What did you get when you foiled it after you plugged in -x? Yeah. Yeah. Okay, so you got this that we got here. Okay, so is that so you got that before we plugged in the negatives? Okay, I would double check the your signs as you're going through. You might have done like x. I would double check because it should be the negative and then the positive. Yeah.
I filled the negative x.
So you plugged it in first and then started running. I would save it to these. Mostly just because it'll be easier to compare. It's easier to plug -x into this than it is to look at -x when it's plugged in. Just a little bit simpler. Because here, looking at what we have, what's going to happen when I plug in -x? So the -4x bit is going to act like an odd function. It's going to change to a +4x. What's going to happen to my x squared? It's going to stay the same. And what's going to happen to my +4? It's also going to stay the same. So this bit's going to act like an even function. This bit's going to act like an odd function. And then this bit's going to act like an even function. So is it behaving like an even function, an odd function, or neither? It's behaving like neither, right? It's like a mix of the two. And the fact that it's all mixed up like that, like if I give you a positive plus a negative plus a positive and ask you what we end up with, you're not sure. Right? We can't say definitively, yes, I know exactly where we are. And so here, this one does not quite behave in either way. It's tempting to say both, right? It's tempting to look at this and be like, oh yeah, some of it's like even, some of it's odd, or yeah, some of it's even, some of it's odd. So both would maybe feel kind of nice, but there is no both. You can't have a function that is odd and also even. There is only even. What happens when we plug -x into x squared? What's going to happen to it? And it's going to become square a negative number and it becomes positive. What's going to happen when we plug -x into this -4x? We're going to get +4x. So this stayed the same. This switched from negative to positive. And then what's going to happen to the +4? It's going to stay the same. So stays the same, switches, stays the same. Which means that some of it's acting even and some of it's acting odd. So it's yeah, Ashton. Yeah, on the classroom.
Yeah. Like it's just.
Just like f of x equals 12. Negative 13, sure. So what's gonna happen when you plug in negative x? It's not gonna change, so what kind of function? Yeah. Yeah, that one I tried to make it a little, not even like tricky, just like fighting against our urge for what it means to be even versus what it means to be odd by making it negative. The fact that it goes from negative to negative means it stays the same. And by making it an odd number, that doesn't happen, right? The function itself is big. Absolutely. And then if I just give you a constant, for instance, asking what's the power of the x that's attached to this 4, which feels weird because there isn't an x. What are you talking about? What's the like invisible power that I can look at there? X to the what? Well, x to the first power would be like this. X to the 0th power. What kind of number is 0? It's an even number. So anything raised to the 0th power, any function that has x to the 0, which is just constant, right? That's just 1, is going to fit our definition of. Here's kind of. So constants are like x to the 0. It's like 4 times x. So it works out.
Wait, how'd you get C? And for C?
Yeah. So C, you could either do out the multiplication, which is totally fine. So you could literally multiply this function by the other function. So f times g. Or what we kind of did generically is if we plug in negative x right here. What happens when we plug negative x into our even function here? Is it going to become negative or is it going to stay the same? Stay the same. What happens when we plug negative x into our odd function? Is it going to become negative or stay the same? Become negative. So we have something that stayed positive times a negative. So what's a positive times a negative? A negative. And so plugging in negative x gave us a negative because it was positive times negative. And so it's odd. And that's true for any even function times any odd function. You're always going to end up with an odd because a positive times a negative is always negative. And again, if it was odd times odd, it would be positive, therefore even. Yeah, think of like odd and even functions as like positive, negative. Good question. Other questions here? Other questions with evens? I have less time to work on the classwork than I was hoping, but that is what it is. We'll definitely have time tomorrow. Tomorrow's lesson is short. Okay, and I do want to. I need us to finish 1-3 today. The final kind of piece to the puzzle. It's a very hodgepodgey puzzle. Unit 1 is kind of, a little bit disconnected, just trying to throw in a bunch of things. Is the idea of a piecewise function. Piecewise function. So most functions that we run into, the vast majority of functions that you guys work with, have a single equation that defines the function over the course of its entire domain. Right? We might say from negative infinity to positive infinity, my function is going to behave like x squared. Or from a negative infinity to 0 and then 0 to infinity, it's going to behave like 1 over x. I just have to throw away 0 because it would make me divide by 0. Things like that, right? Generally speaking, we like to look at a single function at a time and just work with what we have. That doesn't necessarily need to be the case, though. We can actually work with what are called these piecewise functions, which are functions that behave differently, that follow different rules, depending on which set of x values, which interval you're focusing on. Yes, Trey. Yeah.
But I do know that piecewise functions, you said they behave differently. So like it'd be this equation if x was greater than zero or equal to 0, or this function, it would be this equation if x is less than 0. But I don't know how to set the equations, get them to the piecewise definition.
Yes, we're gonna take a look at this. Specifically, we're gonna focus on absolute value functions as piecewise functions, and we're gonna do exactly kind of what Dre just communicated here, which is we're gonna figure out, okay, how do we communicate this as piecewise information? Because honestly, absolute value functions are kind of hard to solve otherwise. Absolutely correct. Okay, so piecewise function, we'll just say that this is a function that, and honestly, like, I think the kind of casual definition of like a function that follows different instructions, or that has different definitions, follows different instructions for different intervals of x is actually a pretty good kind of idea of what this is trying to communicate. So a function that follows different instructions depending on the value of x. So like maybe we say when x gets pretty big, we want to behave like negative x. But when x is pretty small, we want to behave like x squared. And when x is kind of negative, we want to behave like the cube root of x, or something there. We just follow various instructions. Okay. It's piecewise. It's kind of broken up. Now, a fantastic example of a piecewise function, and the one that we are really going to kind of highlight and focus on, is the function that f of x is equal to the absolute value of x. Right. Now this works somewhat well as just kind of a normal definition for what we are working with. Like, yeah, I can graph this, I understand kind of what this looks like, but to really kind of do math with absolute values, you really do need to understand its piecewise nature. So we are considering this function here. It's going to look like this. That. What do we notice about this function? So no curve, right? We kind of had, and this is actually why we need to define this piecewise function for calculus, right? There is this idea in calculus of having a smooth curve, right? And when we looked at x squared, we had a really nice smooth transition from going from like positive, and then we kind of slowed down and we passed through 0, and then we kind of went back up the other direction. That's really important for calculus. Right? Calculus is all about like looking at slopes at various points, and having a nice, literally what is called smooth curve is important to them. This function here is smooth everywhere except where? 0. And at 0, we kind of abruptly, really sharply turn. We like rotate 90 degrees really, really, really fast, and then shoot off in a completely different direction. So if I ask you like, okay, what slope is going on at this point? You can't say, because to the left, it's doing one thing, and then to the right, it's doing something completely different. That's a problem. That's why we might want to define this as a piecewise function. Okay, so what's going on? So we're actually going to go through this. We essentially have two different behaviors that are separated at 0. We have one behavior that's everything to the right of 0, one behavior that's everything to the left. So that problem point kind of highlights exactly what's going on. So what is happening when my x is a positive number? What rule am I going to obey? What does my function do? f of x is just the same as. Yeah, so f of x is the same as y, but then what happens if I just plug a positive number and take the absolute value of it? What happens to that number? It stays the same, right? F of x is just x. And our output, when you plug in a positive number, is just the number you plugged in. In particular, you could think of this as like a line with a slope of 1, but I think kind of that intuitive understanding of like our output when I plug in a positive is just that it stays the same is a pretty good one. It creates a line with us. Okay, but what's going to happen if I plug in a negative number? So if x is less than 0, what are we going to get? So let's say I plug in -2. What's going to happen to my number? It's going to turn positive. How could I accomplish? How could I force a negative number to turn positive? Okay. Squaring it, but let's say I don't want to change. So squaring it's not a bad idea at all. Let's say I don't want to change the size of that number. Multiply by -1. So if I start with a negative number, which we are guaranteed to do if I'm following this rule, right? Saying if the number is negative, here's what we do. And what we can do to make it positive, squaring it wouldn't have been a bad idea, but not change the sign is we can multiply it by -1. And so notice the absolute value function follows two different rules depending on what side of the y-axis you are. Right? If we are a positive number, our function says stay the same. If we are a negative number, our function says, hold on a second, you need to become positive, multiply by -1. See what you end up.
Still in negative x is less than 2.
Yes. So we're saying if it's less than 0, which means if it's negative, we're going to take our negative number and we're going to multiply it by -1 to turn it positive. And so exactly your idea of if I want to keep the size the same, multiply by -1, and we should be gold. Yeah, Ash. Why did I arbitrarily decide to do greater than or equal to here rather than less than here? Certainly there are some instances where it would matter. But because this function is continuous, it actually doesn't matter. So because 0 could adhere to either rule, right? 0 is going to stay the same if I do nothing to it, but it's also going to stay the same if I multiply it by -1. I could have done less than or equal to 0 here and greater than, strictly greater than here, and I would get the exact same. So really, really good question. Sometimes it is relevant. It's not going to be relevant if we have this kind of like nice trade-off at the same point where we get a nice connected graph. Where it could be very, very relevant is if, my other graph like started here and then, came up like this. Now, all of a sudden it matters a lot where 0 is defined. And in particular, it is not defined for everything that's going on to the right. It would only be defined by what is going on. So it's definitely something to pay attention to. Here, you could do either. I would avoid doing both. You wouldn't be wrong in doing both. Just because like kind of that same idea of like if I say that 0, 0 is a point and then I say that 0, 0 is a point, like I haven't contradicted myself. It's just kind of awkward. And so you're not going to run into like any function definition issues, but I would just pick one if they meet up and run. But really good. Yeah, I just flipped a coin in my mind. Yeah, very good question. Other questions here? This is kind of more of like a broad topic overview and just like I want you to see this as a piecewise, and we'll look at what is going on with our kind of like piecewise functions right here. Okay. So in this case, example 3, I have given you a whole bunch of absolute value equations. Ultimately, our goal is to solve absolute value equations. And I've given you 2 tasks. I first want you to write them as piecewise equations. And then I want us to actually go about solving these piecewise equations. All right. Let's start with A. And so we are taking the absolute value of x plus 4. We want to know when this is going to be equal to 7. Let's start with our piecewise definition here. All right. So what is the tipping point going to be? This is kind of a nice question to ask with these algebras. What's the tipping point where I'm going to switch from positive to negative? Okay. We'll work on the 7 thing. I'm just focusing on the left. So when does my absolute value? Because we said, okay, absolute value is going to behave one way for positive numbers, at least positive numbers alone, and it messes around with negative. So we need to be able to know when is our function going to be positive, when is our function going to be negative, to be able to kind of piece together, okay, what would this look like as piecewise? So when would we, essentially, when do we become 0? When do we switch from being positive to negative? Yes, what is the value of x at which that starts to happen? Just negative x wouldn't necessarily do it for us. It's not any negative number. What happens if I plug -1 in for x? -1 plus 3, just 3? That would just stay the same. What's the first kind of negative number that when I plug in, it starts behaving differently, or potentially starts behaving differently? Anything below negative 4. Right, so -4 is the cutoff point. That's when the inside of our absolute value switches from being positive. Do we see that? That this is going to be positive with any value of x that's more than -4. It's going to be negative with any value of x that's less than -4. In fact, we can go ahead and state that this function f of x would be equal to, this is going to be, it's going to stay the same, right? It's just going to be x plus 4 if we said to the right. And again, you could do just greater than, or you could do greater than or equal to. Either way is fine. And we said we'd be the negative version. We multiply by -1 if we are to the left. We are effectively just going to solve both of these for x. We're going to treat both of these equations and solve each one for x. So actually defining where this is going to be relevant is a little bit less important here. It's not bad practice. It's just not as relevant as, okay, it could be. Okay. So let's use our two definitions. Let's figure out when this absolute value of x plus 4 is going to be equal to 7. Our first definition says that I should do what with x plus 4? Leave it alone, right? We're going to leave it alone. X plus 4 is just going to stay as x plus 4. We're just going to solve the equation x plus 4 is equal to 7. Really quick, just double check here. When does this happen? For what values of x does this definition apply? Anything, well, okay, we're going to solve it and it's going to be 3, but what must be true about x according to our piecewise definition? It must be greater than -4. So as long as the answer we get here is greater than -4, we're in the clear. We're good. That's a goal. All right, so subtracting 4 from both sides, what do we get? We get 3. Right. Is 3 in fact greater than or equal to -4? Yes. So we have successfully found a solution with this particular definition. So 3 is one of our solutions. Okay. What's the second definition that we should check? The negative version of it, which is only going to happen when x is less than -4. Okay. So we need the negative of x plus 4 to be equal to 7. How would you guys go about solving this? There are a couple of different You divide everything by -1 to make this positive, and then solve. What else could we do? We could distribute the negative. Either way works. Either way is great. Whichever you prefer, whatever kind of speaks naturally to you. I would probably divide here by the negative first, but it doesn't matter. Either way is fine. So we get that x plus 4 is equal to -7. And subtracting 4 from both sides, that x is equal to -11. Okay. First of all, let's check to make sure that this is a valid solution. Right. Do we fit this definition if we are at -11? Yes. Notice -11 is in fact less than -4, and so we are good to use this definition for getting this solution. And so x equals -11 is in fact a valid solution. It's kind of a nice little gut check to make sure that. Questions here with our absolute value function. Okay, I want to take a look really quickly at C. And then we'll do B and D tomorrow at the start. I want to show us B as well, but we'll do that at the start of class tomorrow. But I do want to kind of highlight what's going on with C. So C, we've got a little bit of extra stuff going on. My advice would be to solve for the absolute value part before you make your kind of piecewise adjustments. So get the absolute value on its own, and then kind of work from it, if you are able. So here, what would I do to both sides in order to get the absolute value on its own? Divide by the 2/3. That would absolutely work. What is dividing by 2/3 the same as? Multiplying by 3/2. Very nice. So the absolute value of x minus 7 should be equal to negative divided by 2, -12. Let's pause right here. What are we being asked to find? Like what is this equation basically telling us? So we're going to take the absolute value of a number, and what are we going to end up with? -12. Does that make any sense? Is it possible for us to take the absolute value of a number and end up with -12? No, can't be. So what are the values of x that would make this statement true? There are no values of x that would make this statement true. This would be no solution. Now, what's our cutoff point here? When do we switch from being positive to being negative? When does the inside of our absolute value swap? When is it 0? When is x minus 7 equal to 0? When x equals 7. So anything greater than 7, we're going to be plugging in a positive and it's going to be staying the same. Anything less than 7, we're going to be plugging in a negative. It's going to be switching. If you were to solve this, you would get that, and you can try, you can go ahead and try. You would get, if you use the definition that we can only use when x is greater than 7, you'd get a value that's less than 7 for x. Okay, so that one would work. And if you were to solve this using the definition that only works when x is less than 7, you would get a solution that is greater than 7. And so, okay, that one also can't work. Okay. If we were to just try this, the definition that works when we're greater than 7 is leave it alone. And the answer that we get is x equals -5, which doesn't happen. We don't leave things alone when it's going. All right. Good work today, you guys. I know that was a little longer than we anticipated. Tomorrow's lesson is going to be fairly short. And we'll have time for fun. Which I keep that. Have a fantastic rest of your day. And I will see you all tomorrow.